Hello, students of chemistry, students of science. Let's talk about colligative properties. Colligative properties are properties that only depend on the concentration of a solute that are in a solution. And why am I playing with this molecule? You might be wondering. Well, this is ethanol. And this is going to be one of the solvents that I'm going to be mentioning today as we do a practice problem. So I wanted to make this video as part one of a series because there are three primary colligative properties. There is boiling point elevation, there is freezing point depression, and there is osmotic pressure. So I figured we'd make 3 videos talking about each one of them. Okay, so let's get to it. Alright, which pen should I use? You know, I almost always use this one because it's thicker. I feel like you can see my writing a little bit better. Alright, so colligative properties, part 1. So we're going to start with freezing point depression and boiling point elevation. And the reason for that is these go together. I'll just talk about one of them in this video and the other one in the next video. And so why don't we start with boiling point. So notice how if you have a solute in a solution, and I will do a short review of when we're talking about solution, what's in it. And so if you have a pure liquid versus a liquid that has a solute in it, something dissolved in it, the boiling point will go up. Meanwhile, if you were then to measure the freezing point, it would go down. So we call that freezing point depression. It is depressed. Very sad. Okay. Part 3 seems a little bit like an outlier, but the reason why we keep all these 3 together is that all 3 of these, they depend only on the concentration of the solute, not its identity. Okay, so it just depends on how many particles are dissolved in that solution. That's the thing that is going to cause the boiling point to go up in a very predictable, calculatable way, or the freezing point to go down, again, predictable, calculatable way, and the osmotic pressure will change, will go up as the concentration of the solute particles go up. Okay, so let's just talk a bit about, so we're very clear on this, solute, solvent, and the solution itself. Okay, so when we have a solution, so I'll draw my little beaker here. Alright, and it's got some little graduations on it. Of course, if it's a beaker, it's not the best at measuring, but it's very good at holding solutions, right? Okay. So the bulk liquid, this is our solvent, right? Okay. The particles, which are usually invisible, cannot see them with a naked eye, those particles that are dissolved in solvent, that's our solute. This can be a gas that's dissolved, it could be a liquid that's dissolved, or it could be a solid that's dissolved. Okay. And so this whole thing with the solute dissolved in solvent, that is our homogeneous mixture. All right, of the solute with the solvent. Okay, now concentration units. If we are talking about boiling point elevation or freezing point depression, that means we are changing the temperature. And we cannot easily describe what is the concentration with molarity that's in moles per liter, because the solvent itself may expand or contract with different amounts of the solvent, because the temperature changing can then cause the density to change. All right, so what we can do is we can express the concentration for these two examples where the temperature is changing. Okay, so this is for the boiling point elevation and the freezing point depression. We will use lowercase italicized m. This is molality. And this is moles of the solute per kilogram of solvent. Okay, so we are using mass, not volume, that you use with molarity. Okay, so just as a reminder, not molarity, which is moles per liter. And when we say moles per liter, we mean moles of solute over liters of the entire solution. The solvent with the solute dissolved in it. Okay, this is volume. We're not using this for boiling point elevation, freezing point depression. Okay, so again, molality works great for this because the mass will not change as the temperature changes. Okay, so now let's take a look at what is happening here when we have boiling point elevation, freezing point depression. And as an overview, I want to look at a phase diagram. All right, what is a phase diagram? Well, as you investigate the change in temperature versus the change in pressure of any compound, okay, we can go way down low temperatures and very low pressures and investigate this compound and see Is it a solid, a liquid, or a gas? And express the phase depending on the compound itself. So, phase diagrams, they will be different depending on what the compound is that you're interested in. And when we're talking about freezing point depression or boiling point elevation, we are really looking at and interested in the solvent itself and how the temperature and the pressure affect its phase, whether it is going to be a solid, liquid, or gas. Because what are we looking at with boiling point elevation? We're looking at a phase change, right? When something boils, what's happening? If it's boiling, it's going from what phase to what phase? Liquid to gas, right? When it freezes, what are we looking at? We're looking at liquid to solid. So, with these two colligative properties, we're interested in phase changes, and so that's why a phase diagram is important to consider. Okay, so phase diagram, this is unique to each compound. All right, and again, specifically, we are interested in the solvent, whatever that might be. And usually, if we're doing things in environmental chemistry or biological systems, the solvent is usually water, but it could be anything, right? So, very generally speaking, we have phase diagrams that look something like this, okay? So depending on your axes, if we are starting with 0 pressure and perhaps if it is 0 Kelvin, of course you could start temperature higher than that, but we're going to see a separation, look something like this. And then, again, depending on the liquid, when it's in the liquid phase part, depending on the compound, we will see different behaviors of whether this line is sloped this way. Sometimes it'll be more straight up and down, and it can even slope this way, which it does with water. So we've got some different possibilities. Again, it's unique to each compound. All right. Over here, higher the pressures, higher likelihood we're going to see solid phase. So temperatures go up, low pressure, we would expect to see gas phase. And here is where the liquid phase shows up. Okay. So as you learn more about phase diagrams, you learn about things like this is called the triple point, where at exactly that pressure and temperature, you will have all 3 phases in equilibrium and things like that. So there are aspects to this. But I want to focus on what we are interested in with our colligative properties. Okay, so I'm going to get another color here so we can see a little bit better what's happening. Now, the last time I tried using my red ink, it bled all over my finger, so I'm going to use the blue ink here. Okay. Because what we're interested in everyday life is 1 atmosphere pressure. Okay? So, let us consider what happens here. Let's see, let's say I kind of wrote pressure around where I wanted to put 1 atmosphere. So, how about if I do it about right here? Okay. So, if this is 1 this particular compound, if we extrapolate 1 atmosphere pressure over, this is for the pure liquid, it means that this is the temperature at which the phase changes from liquid to solid if we are getting lower in temperatures, or if we're starting low temperatures, it means this is the point where, as we increase the temperature, the phase would change from solid to liquid. So in other words, this is the freezing point, right? This is the freezing point at 1 atmosphere pressure. So we could call that TF if we wanted to say, hey, that's the freezing point. So what about here, where we extrapolate over, and if this line is signifying this is where this compound changes from liquid phase to gas phase, if you cross this line, that means at 1 atmosphere pressure, here is where we get the boiling point. This temperature is the boiling point. Okay. Now, what happens when we take this liquid and we dissolve something in it? We dissolve particles into it and create a solvent. Create a solution. All right? Well, what happens is, down here at these lower temperatures, if we look at the liquid that's trying to freeze, but there are solvent particles in the way. You could think of those solvent particles of getting in the way. The solute is getting in the way of the solvent molecules trying to assemble themselves into the solid phase. All right, and what happens is it takes a lower temperature for that to be able to happen. And so ultimately, what happens is that if you have, gosh, I wish I had another color. I'm not trusting this red, but let me take a look. Looks a little sketchy. Okay. All right, I'm going to press my luck though. Okay, what happens is the liquid part of the phase diagram is expanded. Okay. It looks like this. Now this is just a rough sketch, of course. It's not like, doesn't have exact numbers with it. Okay. So this now is the phase diagram for a solution. When we have now added in particles, solute particles, this phase diagram would be for solution of a specific concentration. All right, if you increased the concentration, this would continually get larger and larger. Okay, so I've just arbitrarily chosen a certain concentration that would result in the expansion this far. Okay, and what that means is, look at this. We have a new boiling point. This is at 1 atmosphere pressure still, but we have now expanded the liquid phase by dissolving in these solute particles. It is now more difficult for those solvent particles to escape. All right, the vapor pressure, if you've learned about vapor pressure. All right, so we now have a new boiling point This is of the solution, not the pure solvent. And what has happened here is we have now a new freezing point for the solution. So check this out. We have boiling point has gone up, boiling point elevation, and here the freezing point has gone down, freezing point depression. Okay, so this is essentially the background of when we do carry out calculations. Okay, and you can calculate what is this difference. What is the difference in the temperature at which it boils? That can be calculated. Likewise, the temperature difference where it freezes can be calculated. And this is based on the concentration of solute particles. As I mentioned before, this whole idea of colligative properties is something that depends only on the concentration of solute, not its identity. Therefore, we can calculate this change. Let's look at this one. All right. By how much did that freezing point change? Okay, so this difference here, it depends on that solvent, and it has a constant that is associated with this particular solvent. All right. It's the, in this case, it's the molal freezing point depression constant. So it's a very specific constant based on the molality of this solution, and we multiply it by the freezing point depression constant for that solution, for that solvent. Okay, so this is a number that is specific, unique to each solvent. Okay, so it's something we can look up and find out what is our solvent, what is the freezing point depression constant. And if we know the concentration in molality, we can find by how much was that temperature depressed or reduced. Okay, so same thing here. Difference between these two, delta, and now when we're looking at boiling point, here we would need to know for that solvent, what is the boiling point boiling point elevation constant, and multiply that by the molality. And again, this is unique for that solvent that you're working with. Okay. So let's do an example so you can see how this works. Okay. And ahead of time, I thought, hey, let's make, instead of water, let's make ethanol our liquid solvent that we're working with. And we can see what is we'll choose one of these. Boiling point elevation, I decided would be part 1. So let's do that. Okay. All right, so let's flip this over, get a clean sheet. this will be boiling point elevation. And let's look at if we were to have and it kind of depends on what you are dissolving into what, right? Okay. But we could say that we've got a solution of, and here we need to know what is the molality, okay? So that needs to be either given to you or it's something that you can calculate, all right? So we're going to say that we have a 0.25 molal solution of water. So isn't this odd? We have water. This is the solute in ethanol. So you always want to be really clear on which one is the solute and which one is the solvent. So you'll always carefully read the problem itself, okay? And we want to consider each one of these following questions. And one is, what is that boiling point elevation constant for ethanol? Okay, and then let's also ask, what is the boiling point of pure ethanol? Make sure these two questions are clear. And then let's ask the main question, is the boiling point of the 0.25 molal water solution. And again, I'm going to write out that it's in the ethanol solvent, just so we're super clear on which is the solute, which is the solvent creating this solution. Okay. So I wanted to, again, just to be very clear what's what, these two questions we need to look up in a table, or it will be given to you. All right, this is not something that you can calculate. These needed to be measured by someone else ahead of time. So this is information that you'll need. So the normal boiling point, okay, and the boiling point elevation constant. I'm going to look those up. And it is 1.22 degrees Celsius per molal. Okay, this is the unit for the boiling point elevation constant. And it needs to have these units so that molal will cancel out. And we're going to be working in degrees Celsius, not in Kelvin. And the reason for that is that these boiling point elevation and freezing point depression problems, these are very day-to-day things that you would measure with a thermometer, a regular thermometer. They don't need to be absolute, okay? And so typically the convention is we work with Celsius. Okay. So what about the regular boiling point for pure ethanol? Again, we can look that up, or it can be given to us. 78.4 degrees Celsius. Okay. All right, fabulous. So now, what do we got? Well, we can now figure out what is the new boiling point of this solution. Okay, so the change in the temperature of the boiling point we discovered on the previous page is given by a very straightforward mathematical relationship, which is the product of the boiling point elevation constant for ethanol multiplied by the molality. Okay, great. So we have here the boiling point elevation constant. Excellent. 1.22 Celsius per molal. And we can multiply that by the molality, which was given in the problem, 0.25 molal. 5 molal. Okay, fantastic. So here is the change in temperature. Let's grab the calculator. Oh goodness, I love this. I do this every time it does this. I always want to show you. I don't want to clear it out before the video begins because this is so amazing. I swear I have gremlins in my calculator or aliens. I don't know, but I always get this funky stuff showing up every time I let my calculator sit for too long with no action. It just kind of creates these very bizarre. I can't even say their numbers or letters. I don't know what they are. Okay, but let's clear it out and get going. We are figuring out the product between these two. 1.22 times. Times 1.22 times 0.25. Okay. Alright. I am going to, for a moment, well, look at this. We have 3 sig figs, 2 sig figs. We are limited in significant figures by the 2 here. So I'll round this up. 1 molal cancels, so we have degrees Celsius. Okay. So this is not our final answer, is it? Okay, so let's take a look here. What we just figured out is this is the change in temperature. So we need to reason through, is this temperature greater than the normal boiling point of pure ethanol, or is it 0.31 less than the normal boiling point? And the answer to that question lies herein. Lies in the fact that we know that the boiling points are always getting elevated. They are going up. So by virtue of asking about the boiling point, it means that this change is this much larger than the boiling point of pure ethanol. All right, so that means that the new boiling point, okay, or in other words, of the solution is our normal boiling point, 78.4 degrees Celsius, plus 0.31 degrees Celsius. We could probably do this in our heads, but let's use a calculator. Okay. 78. Now remember the rules of significant figures with adding and subtracting. We only get to go past the decimal point here as many as the one that has the smallest number of places past the decimal point, which is, we're limited by the tenths place here. So that's all we're going to get. Alright, so here is our new boiling point. It has gone up to 78.7 degrees Celsius. Alright. Well, I will make another video with freezing point depression. I will also make a video with osmotic pressure. And once again, here's our little ethanol molecule that we were investigating. This is our molecule that has this boiling point elevation constant and has this boiling point low ethanol. Looks like a little doggy animal. Alright, well, thank you so much. I hope this was helpful. Please do let me know in the comments if you have other questions, want any clarifications, if you have any requests for other topics in chemistry you would like me to cover. Please do let me know. And also, I would so much appreciate it if you wanted to share this material with other people that might find this helpful, this very slow, methodical way of teaching these kinds of problems in mostly general chemistry, although I do teach some organic chemistry, a little bit of biochemistry, sometimes some upper division inorganic chemistry, just depending on what requests I get or what I'm feeling like that day when I make my videos. So liking and subscribing always helps also. So I very much appreciate all of you who are here and who support this channel that is ever so slow growing, but I do feel that I am providing a lovely service for so many students and other people who maybe aren't formally students but just enjoy this. So I'm very happy to be here and I appreciate all of you. And I will see you again next time.